Hello class, and welcome to this second day of section 6.1, which is going to cover some more rules of exponent properties. By the end of today's lesson, you will be able to use the exponent properties to solve equations with rational exponents. So what do I mean by rational exponents? These are exponent values that include a fraction and or a variable expression. So the exponents that we were looking at in the first video, so say for example 3 to the 4th power, that is just a regular whole number, or even if we had 3 to the negative 4th power, we were talking about those negative exponents, that's going to be an integer. Now we're going to talk about what happens when we have a fraction in our exponent, or when we have some sort of variable expression in our exponent. When it involves a fraction, this is a way to represent a radical expression. What do I mean by radical? The radical that you are familiar with is square root. So square root, this symbol right here, without the 4 in it, this symbol right here is what we call a radical symbol. The root that you are familiar, or the radical that you're familiar with, is the square root. We can also have the third root, or we can have the 10th root. So these are different types of radicals that we can deal with. One way, the reason we say that this is a way to express radical expressions, we can write the square root of 4 as 4 to the 1/2 power. So that's how these are related. To give you a more explicit definition for how to use this, if we've got the radical of m, figuring out the a to the nth power, what we do to write this with our rational, our fraction exponent, is we say a to the n over m. So whatever the exponent is the numerator of the fraction, and whatever the radical power is, that's the denominator of our fraction. So when we come down here to this one, when we have radical of 2, if there's not a number in the front, the radical we assume is 2. So that's the square root. So if there's no number in the front, we assume it's a square root, and that's 2. If there's no exponent behind the number, the exponent is going to be 1. So the square root of 2 is the same as 2 to the 1/2 power, because we have our power of 1 and our root, or our radical, of 2. If we come down to the 6th root of 7 to the 2nd power, we would say 7, and then we have our exponent as the numerator, 2, over the denominator, which is 6. So we're currently at 2/6, which can be reduced to 7 to the 1/3 power. So if you ever end up with a fraction as the exponent that can be reduced, you always want to make sure you reduce that down to its simplest possible form. Go ahead and try this one on your own, writing the radical as a rational exponent. We end up with 3 to the 5/4 power. Next thing we're going to talk about is how we can solve with rational exponents. So right now you see we've got 3 to the x over 2 power times 3 to the x over 3 power equals 3 to the 9th power. So this is where it's important that we remember those rules for exponents from our lesson yesterday. Remember, if you are multiplying with the same base, so 3 to the 4th power times 3 to the 5th power, ultimately ends up as 3 to the 9th power. If you were taking a power and raising it to another power, we would have ended up with 3 to the 20th power. If we were dividing, remember you subtract those exponents. So 3 to the 9th over 3 to the 7th would give us 3 to the 2nd power. So those are the key rules we need to remember. So now we're looking at our base here. We've got 3 and 3. These values are being multiplied, so that means our exponents here are being added. So we've got 3 to the x over 2 plus x over 3 power equals 3 to the 9th power. Now, the nice thing about this is our bases are the same, so we can essentially ignore those for a minute. So we're just going to look now at the exponents to get an equation to solve. So I now have x over 2 plus x over 3 is equal to 9. Remembering back to our basics, in order to add fractions, we need a common denominator. In order to get a common denominator between 2 and 3, our answer is going to be 6. So this first fraction needs to be multiplied by 3. Second fraction needs to be multiplied by 2. So I end up with 3x over 6 plus 2x over 6 is equal to 9. Then because they have a common denominator, I can actually add those up. So that's going to give me 5x over 6 is equal to 9. And then I'm going to go ahead and continue to solve this problem. If I've got 5x over 6 equals 9, in order to get rid of that 6 in the denominator, I'm going to multiply by 6 on both sides, and I get 5x is equal to 54. And I'm going to finish by dividing by 5 on both sides, giving me x is equal to 54 over 5. You do not want to turn these into decimals because we are looking for these rational exponents. We're looking for them as fractions. So our x value here is going to be 54 over 5. Go ahead and try this one on your own. When I do this, again, we've got the same base. We add to get our exponent, and then we set it equal to the other exponent because all of our bases match. Get our common denominator, get rid of that denominator by multiplying, and then divide by the numerator, giving us 36 over 5 as our x value. Next thing we're going to look at, what happens when the bases aren't the same to start? When you are looking at these problems, if the bases are not the same to start, we have to find a way to make the bases relate. So we have to see how 3 relates to 27. Again, we have to do this by exponents. So 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. So that's how these two values relate. So instead of writing 27 right here, I'm going to change it to its exponent form. So I'm going to say 3 to the third power to the x minus 4 power is equal to 3 to the 2x minus 6 power. So we've taken this 27 and we've rewritten it so that our bases, 3 and 3, match. Now what do I need to do from there? On this left side then, it becomes a power of a power rule. So we need to multiply. So on this side, we end up with 3 to the 3x minus 4 power equals 3 to the 2x minus 6 power. Again, now that our bases are the same, we can ignore those and look just at the exponents to be able to solve our equation. So 3x minus 4 is equal to 2x minus 6. Combining our x's, we're going to subtract 2x from both sides, and I'm going to be left with just x minus 4 is equal to negative 6. Next step is going to be to add 4 to both sides, and I end up with my answer of x is equal to negative 2. So again, when our bases don't match, we need to find a power that allows the bases to become the same. So we used 3, that's the smaller base, figured out what exponent was going to get me to 27. Once we did that, we used our power of a power rule to get the exponents into an equation. The bases are the same. We can now set the exponents equal to each other and solve for x. Go ahead and try this one on your own. We needed to figure out what power it was. 4 was the smaller one, so we ended up with 4 to the 4th power. We had that distributive property on the exponent, giving us 4x plus 8. Now that our bases are the same, we can set the exponents equal to each other, and we solve to find out that x is equal to 1. Next thing we're going to talk about, what happens when the bases do not match, but the exponents match? So if the bases don't match, but the exponents match, we can still combine them because the exponents are the same. When we do this, we're going to combine it by saying 6x to the 1/3 power. So both of them are being raised to the 1/3 power, so I can combine it, multiplication, combine them being multiplied into one group, and that's still going to equal 15. Now, this is something we haven't dealt with yet, is how do I get rid of an exponent? In order to get rid of an exponent, you're going to take the opposite side to the reciprocal power. So because I had 1/3 as my original exponent, in order to move it to the other side, I'm going to raise the other side to the reciprocal, 3/1. Because if I have 1/3 and 3/1, that gives me 3/3, which cancels out to 1. So when you raise the other side to the reciprocal, those values cancel. 3 divided by 1 gives us 3. So now I have 15 to the 3rd power, which is going to be 3,375. And then left over on this side, I have just the 6x. In order to finish this problem, I'm going to divide both sides by 6, and I end up with x is equal to 562 1/2. So again, if they have a matching exponent, combine the values. If they were being divided, then you would divide those values. In order to get rid of an exponent, you move it to the other side by raising that side to the reciprocal exponent, flipping that fraction over, and then you continue to solve like a normal equation. Go ahead and try this one on your own. So we combine, raise it to the reciprocal power, which is just to the 2nd power, divide by 8, gives you an answer of 18. Last thing we're going to look at is when we have some division going on. Again, when you combine these, you need them all to have the same base. So our bases right here are 2, 32, and 16. 2 is the smallest one. So we're going to use 2 as our main base. So 2 to the 1st is obviously 2. 2 to the 2nd gives me 4. 2 to the 3rd gives me 8. 2 to the 4th is 16. So that relates to that one. And 2 to the 5th is 32, which relates to our top part. So we're going to rewrite this now with our matching bases. So 2 to the -4/5 power stays the same. Then over on the other side, I've got 32, which I'm going to write as 2 to the 5th power being raised to the x minus 5 power over 2 to the 4th power being raised to the 3/5 power. Now, how do I simplify those? We're going to look at this exponent. Right here, we've got 5 times x over 5, which ends up as 5x over 5, or just x. So now we're at 2 to the -4/5 power equals 2 to the x power over, for this one, we've got 4 over 1 times 3 over 5 gives us the 12 over 5 as our fraction. So I've got 2 to the 12/5 power. Next thing I'm going to do when I'm dividing, remember that means we're subtracting our exponents. So I've got 2 to the -4/5 is equal to 2 to the x minus 12/5 power. We subtracted our two exponents to combine them. Now, because our bases are the same, that means I can set those exponents equal to each other. So I've got the negative 4 fifths is equal to x minus 12 fifths. In order to get rid of the 12 fifths, I'm going to add 12 fifths to both sides. They already have a common denominator, so I can just add those up. Negative 4 plus 12 gives me 8 fifths is equal to x. So again, our process is the same. We need to find that common base. In this case, it was going to be 2. So that stayed the same. 32 turned into 2 to the 5th power. 16 turned into the 2 to the 4th power. We simplified our exponents. 5 times x divided by 5 gave us just x. 4 times 3 fifths gave us 12 fifths. Once I had those in the problem, division meant subtracting my exponents. Once the base matched, I could set those equal to each other, and I get my final answer of 8 fifths equal to x. Go ahead and try this one on your own. In this case, our base is 3. 3 to the 1 is 3. 3 to the 2 is 9. 3 to the 3rd being 27. And 3 to the 4th being 81. So those match up with our original bases that we had. Again, simplifying those, 3 times x to the 3rd gives us x. 4 times 5/3 is 20 over 3. It's all the same, so we can subtract those exponents and set them equal to each other. And when you end up with negative 11 plus 20, you get a positive 9. Positive 9 divided by 3 reduces to an answer of 3. If you have questions about this or anything else from the lesson, please let me know when you get to class.